Hi viewers, welcome to Learning Electrical Engineering channel. In this video, we will see nodal analysis. The nodal analysis in two steps, that is nodal analysis without voltage source and nodal analysis with voltage source. Before proceeding this video, we need to know certain terminology, that is branch, next one is node, and next one is loop. Now, what is branch? A branch represents a single element such as a voltage source or a resistor or any element in the circuit. In this circuit diagram, the resistor R1, R2, R3 and current sources I1 and I2 individually represents the branch. Circuit, the branch can be called as circuit individual elements. Okay, next, node. What is node? A node is the point of connection between two or more branches. Assume that this is the one branch R1 and this is the another branch, that is R2, and the connection of these two branches is called node. So we can write node is connection of two branches. Connection of two or more branches. Okay, next, loop. A loop is any closed path in the circuit. In this circuit, R1, R2, R3 makes a closed loop. So, the closed loop can be called closed circuit. So, correction. The closed circuit can be called as a loop. Okay. What? The closed path in a circuit. Circuit can be called as loop. Okay, now we will proceed further with nodal analysis without voltage source. Okay, in this we will have a one circuit diagram and it has two current sources I1 and I2 and three resistor elements R1, R2, R3 which are connected as shown in the diagram. In nodal analysis, we need to follow certain steps for analysis of the circuit. First, we need to know what is nodal analysis. Nodal analysis provides a general procedure for analyzing circuits using node voltages as the circuit variable instead of choosing the element voltage. Node voltage will reduce the number of equations required to solve the circuit parameters. Now, in this nodal analysis, we need to mark the nodes. We need to follow the certain steps and we will write it here. Steps to be followed are nodes to be marked, node marking, and voltages of the nodes also to be marked. This is the first step, and in second step we need to apply KCL on the nodes to find out the equation required to solve this circuit. And third one is the equation find out by using the KCL we need to solve it. Solving of equation. Okay. Now first we will apply the first step, node marking. Generally in circuit analysis we will mark the ground as the reference node. The nodes are of two types. One is reference node and non-reference node. The reference node will be the ground one. Generally we are marking the ground is a reference node and this is 0, and this node we can mark it as 1, and the node which is available here, that is the connection point of R2 and R3, will mark it as node 2, and the voltage at node 0 will be V0. We will mark it here in this circuit diagram, V0, and voltage at node 1 will be V1, and the voltage at node 2 will be V2. Okay, now the currents need to be marked, and current, we know that the current will flow from higher potential to lower potential only. For that, the current I1 will flow from higher potential V1 to V0, that is, it is shown in this direction, and the current flowing through R2 will be I2. In this we will assume that V1 potential is higher than the V2 potential, so that we have marked the current direction like this, and the current I3 will flow through R3, and the nodes involving for flowing of current I3 will be V2 and V0, and in this V2 is having the higher potential, so the current will flow from V2 to V0 and the direction is downwards. Now we will apply the Kirchhoff's second law as a second step for the nodes. Now how we will apply? So now the number of equations required to solve this circuit are two equations, that is the equations required to solve this circuit diagram is equal to number of non-reference nodes. In this, the non-reference nodes are node 1 and node 2. Okay, the node 0 is the reference node. Otherwise we can say that the number of equations required to solve the circuit is equal to total number of nodes in a circuit minus 1. That minus 1 will represent the reference node. Okay, now first we will apply the KCL to node 1. Okay, KCL to node 1. Node 1. In this, if we see, the incoming current is I1, that is I1 is coming to this node, and outgoing currents are small I1, small I2 and capital I2 are the outgoing currents. As per KCL, the incoming currents is equal to outgoing current. Incoming current in this is that incoming current at node is I1, so we will take it as I1 is equal to the outgoing currents. Outgoing currents, we know that I1 plus I2 plus capital I2. This I1 and I2 are the current sources. Now we will take it as equation 1. Further, we will apply KCL to node 2. So node 2 is available here. In this, incoming current is I2, that is small I2 and capital I2, and outgoing current is small I3. So we can write capital I2 plus small I2 is equal to small I3, and we will take it as equation number 2. So As per the basics of nodal analysis, the number of equations required is equation number of equation required is equal to number of nodes minus 1. This n represents the total number of nodes. Total number of nodes in a circuit. Okay, and minus 1. So in this we are having 3 nodes. Minus 1 is equal to 2. The number of equations required to solve this equation is 2. Now we will apply the current values, that is small I1, small I2 and small I3 individually using the potential difference and its resistance values. First we will find out value of current I1, that is small I1, is equal to, the I1 will flow from higher potential to lower potential, that is higher potential node is V1 and lower potential is V0, and this V0 is equal to 0. So we can write V1 minus V0 by R1, and which is equal to, we know that V0 is equal to 0, so we can write V1 by R1. Second, we will find out I2. So the I2 is equal to V1 minus V2, that is the potential difference between the resistor, that is V1 minus V2 will be the potential available across the R2, and current flowing through the R2 will be I2, and the resistance value will be R2. And in this we are assuming that V1 is higher potential than V2, so V1 minus V2 divided by R2. Next, I3 we need to find it out. The I3 is the amount of current flowing through R3, and the node voltages are V2 and the V0. So the potential difference will be V2 minus V0 divided by R3, and we know that V0 is equal to 0, so the remaining value will be V2 by R3. Now we will apply all the current values, that is I1, I2, I3 in the equations 1 and 2. First we will take equation number 1. So now the equation 1 is capital I1, it is same as it is, capital I1 is equal to small I1. Small I1 will be V1 by R1 plus small I2. Small I2 will be V1 by R2 minus V2 by R2, and the capital I2 will be as it is, we will write, so capital I2. Now on simplification, I1 minus this I2 term we can take to left hand side of this equation, so the equation will become I1 minus capital I2, and we will group the resistance, values of V1 and V2. So when we grouping the V1 value, V1 into 1 by R1 plus 1 by R2 minus V2 by R2. Say this is equation number 3. Fine. Next we will take the equation number 2. So from this equation number 2 we will write I2 as it is. We can write from equation 1. Here from equation 2. So the I2 we can write I2 plus small I2. Small I2 will be V1 minus V2 by R2, which is equal to small I3. Small I3 will be V2 by R3. Now when we grouping this, I2 is equal to this V2 will be remain same, and when we transferring the term V1 minus V2 divided by R2 to the right hand side, it will become negative. So we can write minus V1 by R2 plus V2 into 1 by R3 plus 1 by R2. Say this is equation number 4. Now we can apply the addition method, subtraction method, yeah, elimination method, substitution method, or the Cramer's rule to solve this equation and to find out the values of current, and then we can find out the values of voltages also. For simplicity purpose, we will take the Cramer's rule. So as per Cramer's rule, we will take equation number 3 and equation number 4 to form the matrix. Here we can write the V1 term is 1 by R1 plus 1 by R2 minus 1 by R2, and this is from equation number 3, and from equation number 4 V1 term will be minus 1 by R2 and V2 term will be 1 by R3 plus 1 by R2 will form the matrix of 2 by 2. Then we will write the voltages value, that is V1 and V2, which is equal to the current values. Current values for as per equation number 3 will be I1 minus I2. So we will write here capital I1 minus capital I2. For equation number 4, the current will be I2. We will write it here. On solving this equation by using the Cramer's rule, we can find out the values of I1, I2 currents. Now if we are assuming if 1 by R1 is equal to Z1 and 1 by R2 is equal to Z2, comma 1 by R3 is equal to Z3. This is the conductance. The inverse of conductance will give the resistance. Now we can simplify the above matrix to G1 plus G2 minus G2, and minus 1 by R2 will be minus G2, 1 by R3 plus 1 by R2 will be G2 plus G3, and we will close this matrix, and we will write the voltages values as it is, that is V1 and V2, which is equal to the current values, that is I1 minus I2, I2. Fine. On solving this equation matrix, we can find out the values. This is for without voltage source. Now we will proceed with nodal analysis with voltage source. In this circuit diagram, if you see the a 10 voltage DC source is connected in the circuit, so we can call it as nodal analysis with voltage source. Earlier we have seen the nodal analysis without voltage source, and one more voltage so is connected between the voltages, node voltages, we nodes. One more voltage source is connected between the nodes 2 and 3. In this circuit diagram, if we follow the steps, the step 1 is marking of the nodes. If you are marking that this is the node 0 and this is node 1 and this is node 2 and this is node 3, and we have marked the nodes, and now we need to mark the node voltages. The voltage at node 0 will be V0, and the voltage at node 1 will be V1, and voltage at node 2 will be V2, and voltage at node 3 will be V3. As per this circuit diagram, the current flowing through the 2 ohm resistor is I1, and current flowing through 8 ohm resistor is I2, and current flowing through 6 ohm resistor is I3, and current flowing through the 4 ohm resistor is I4, and the voltage source which is connected between the non non-reference nodes, that is 2 and 3, will form a super node, and it may have the parallel elements also. Still it will form a super node. In this node has some special properties. The super node will not have its own voltage. Super node will not have its own voltage. This voltage source which is connected between the nodes 2 and 3 will form the super node, and this voltage source may have the parallel elements also. Still it will form the super node, and this super node is having certain properties. The first property is it will not have its own voltage, and it will provide the constraint equation. So by using this equation we can easily solve the equation and find out the node voltages. So constraint equation, and the third one is we need to apply KCL and KVL to the super node to find out the voltages. Now to find out the voltage node voltage of V2 and V3, we need to apply the KVL. So in this circuit diagram, if we see the voltage source, node voltage V2 is marked here and node voltage V3 is marked here, and it has the potential of positive and negative is marked as in the as shown in the diagram. Now when we mark the loop initially meets the positive potential of plus 5 volt, so we'll take 5 is positive, and next it will meet the positive terminal of V3, so we will mark V3 is positive, and finally it will meet the negative potential of V2, so we will mark it as negative V2, which is equal to 0. This is the KVL, Kirchhoff's voltage law. On solving this equation, we can find that V2 minus V3 is equal to 5. Say this is equation number 1, and we know the voltage value of the non-reference node is equal to source voltage value, because the voltage source which is connected between the one reference node and one non-reference node. In this, non-reference node is 1 and reference node is 0. So we will take V1 is equal to 10 volt. Okay, fine. Now say this is equation number 2. Now we will apply the KCL to the node 1 and node 2 and node 3, but in place of applying the node 2 and node 3, we will consider it as a super node. So the incoming currents to the super node will be I1 plus I4. These two currents are the incoming currents to the super node, so we will take it as I1 plus I4, which is equal to the outgoing currents of the super node will be I2 plus I3. So I2 plus I3. Now we need to apply the node voltages to find out the node voltages and resistance values to find out the value of I1. To find out the value of I1, we need to apply the potential difference, that is V1 minus V2. So V1 minus V2, this is the potential difference between V1 and V2, and the resistance value is 2 plus The I4 current is here, which is flowing through 4 ohm resistor, and the potential difference will be V1 minus V3, V1 minus V3 divided by 4, the resistance value, which is equal to I2. I2 will be I2 is equal to potential difference of V2 minus V0. We know that V0 is equal to 0, so we will write V2 by 8 plus I3. I3 will be I3 will be uh, correction. I3 is equal to V3 minus V0 divided by 6. So we can write V3 by 6 because the reference voltage is equal to 0. Take this is equation 3. Now on solving this equation, we will find V1 is equal to 10 volt, we know it, and V2 is equal to 9.2 volt, and V3 is equal to 4.2 volt. So we will find out these values. Kindly work it out and check the results. If you like this video, kindly hit the like button below this video. If you not subscribed my channel, kindly subscribe it. If you have any doubts, kindly put it on comment box. I will reply. Thank you so much.